Okay, welcome to another video going through a decision mathematics question. This one is question 4 from the AS Decision June 2024 paper for Edexcel. And we've got a linear programming question now. So figure 4 shows 3/6 constraints for a linear programming problem in X and Y. And we're told that the unshaded regions and its boundaries satisfy these three constraints. So we know we're going to have an inclusive inequality each time because it's including the boundaries. And we need to state the three constraints. So when doing this, we need to really consider what points lie on the line and what gradient each line has. And the first line that comes to my mind is this line with a negative gradient here. So the gradient appears to be -1. So if we're to write the equation of this line, we're going to get y is equal to -x plus some sort of constant. And we don't know what that constant is yet, but we can actually find a point on the line. And it looks like we've got a point 0, 30 on the line. So if we substitute in x equals 0 and y equals 30, we're going to get 30 is equal to 0 plus some number. And that number's going to be 30. So that's the equation of the line. And we can rearrange this. We're going to get that x plus y is equal to 30. But we need an inequality. So we need to consider whether or not a particular point lies on the correct side or the incorrect side of this line. And my go-to point is the origin, or up or along the y or x axis. If I substitute in 0, 0, I can see that's in the feasible region currently. So I know it's on the correct side. So if I use 0, 0, I'm going to get that 0 is something 30. So 0 is either larger than or smaller than 30. It's actually smaller than or equal to 30. So my final inequality is going to be x plus y is smaller than or equal to 30. And we can do these for the other lines. I've got another line. I'm going to use a red pen for this one. And it appears to have a gradient of 2, so y is equal to 2x. If I substitute in the point 0, 10, I'm going to be adding 10 to this. But now I need to consider the origin and which side does the origin lie on. So if I substitute in the origin, it is in the feasible region, and I'm going to get that 0 is some inequality to do with the value 2 times 0 plus 10, which is 10. And I know that 0 is less than 10, so I'm going to combine this inequality with this equality. I'm going to end up with y is less than or equal to 2x plus 10. And then finally, we've got this final line. I'm going to use a purple pen for this one. And this line is a bit of a tough one. We need to calculate its gradient. So we could either calculate it really accurately, finding 2 points and finding the gradient. I've spotted that actually, this is actually using a really formal method. If you go along by 25x, you can go up by 10 in the y-axis. So a change in y, 10, with respect to a change in x, 25, is 2/5. So we're going to get y is 2/5 of x. And then I'm going to substitute in this intercept with the axis. So I'm going to substitute in the value x is equal to 5, y is equal to 0. And if I do that, I'm going to get that 0 is equal to 2 plus c. So c is equal to -2. So I'm going to get y is equal to 2/5 of x, subtract 2, or 5y is equal to 2x, subtract 10. And now I need to consider the origin. The origin is in the feasible region. And if I substitute that in, I'm going to get the 0, some inequality to do with negative 10. And in this case, 0 is larger than negative 10. So my final inequality will be 5y is larger than or equal to 2x subtract 10. Mark-wise, you're going to get 1 mark for one of the equations, another mark for another, and your final mark for the last one. Moving on to part B now, and I just need to move this diagram down a tiny bit first of all. So moving on to part B, and I'm going to use green pen for this one. So the number of fish in the aquarium is subject to 3 further constraints. There must be at least one blue fish. And blue fish is Y, orange fish is X. So if there needs to be at least one blue fish, the number Y has to be at least 1. Y is greater than or equal to 1. The orange fish, X, must not outnumber the blue fish Y by more than 10. So X, there's going to be some relationship between X and Y plus 10. We're told that the orange fish must not be a greater number than Y plus 10. So X can't be greater than Y plus 10. So it has to be less than or equal to Y plus 10. And actually, there's a really good method to try this if you're ever stuck. You can write out some values of X and Y that are on this boundary. So if, for example, I had 15 orange fish, I must have at least 5 blue fish, because the number of orange fish can't be more than 10 greater than the number of blue fish. If I had 22 orange fish, I need at least 12 blue fish. So I can see that X is equal to Y plus 10 here. And then I need to consider which direction the inequality falls. And in this case, this is the extreme value of the orange fish. I can actually have less orange fish, so it can change that inequality. And I'm going to use the same method for the final bullet point. There must be no more than 5 blue fish for every orange fish. So I'm going to write down my X and my Y. For every orange fish, so if I had 1 orange fish, 2 orange fish, 3 orange fish, etc., there must be no more than 5 blue fish. So there must be no more than 5 blue fish for this 1 orange fish, 10 blue for 2 orange, or 15 blue for 3 orange. So I'm actually seeing that Y is equal to 5x here. And reading this bullet point further, there must be no more than 5 blue. So Y is at the largest it can be. So I can make Y smaller, but I can't make it larger. So Y can become smaller if I need it to. So I've got my 3 further constraints, and you'd get a mark for 1 mark for writing the Y is greater than or equal to 1, and 1 more mark for finding the other 2 constraints. And now we need to represent these constraints on the graph. And when doing this, we need to draw the lines with the equality. So I'm going to try drawing these. I'm going to draw Y is equal to 1. So this is actually going to be quite difficult. I've got to get it within a little square. And I'm going to do this now. Hopefully I'm going to get a straight line. I'm not with that one, so I'm going to try it again, because we need to make sure that our lines are straight in decision maths. So here we go. There we go. OneNote's giving me a straight line now. And I've got to cross out wherever the feasible region stops becoming feasible. So I don't want this section below the line. I'm going to draw my next line that I found. X is less than or equal to y plus 10. So I'm going to draw a line x is equal to y plus 10. I'm going to rearrange it. I'm going to draw y is equal to x subtract 10. This is really important because we're really familiar with lines of a form y equals mx plus c. So I know that my y-intercept is going to be negative 10. This is going to have gradient 1. So my line is going to look a little bit, and I'm just going to find a good starting point for this line. The line is going to look a bit like this. There we go. This line has gradient 1 because it crosses the other line of gradient negative 1 perpendicularly, and we see it's passing through point 10, 0. And if we substitute in 10 for x, we do get 0 out for y. So this line we also know is correct. And I need to consider which part of a line I want to be on. So I'm going to test the origin. So the origin, 0, 0, well 0 is less than or equal to 0 plus 10. 0 is less than or equal to 10. So the origin is on the correct side of a line for a feasible region. So the side of the line with the origin in is the correct side. So that means that the other side, over here, we definitely don't like. So I'm going to shade that in a bit. There we go. We've got one final line to add, and that's y is less than or equal to 5x. So it's going to go through the origin this line, and it's going to have gradient of 5. So it's also needs to pass through point 5, 25, which is this point here. And I'm adding that on just to help me draw the line nice and straight. Got to try that on again. Okay, I've got a straight line now. There we go. It's ever so slightly off, but it is within one small square, so this wouldn't be bad for an exam. And because the origin lies on this line, it's a bit tricky. So I'm going to consider the point 5, 5. If I consider a point 5, 5, if I substitute in 5, 5, well, x is 5 and y is 5. I'm going to get that 5 is less than or equal to 25, which is definitely true. So a 0.55 is on the correct side of this line. So everything on the other side of this line is on the wrong side. So I'm going to shade that in just to show that that's the case. So I've now added my 3 lines and I'm left with a feasible region. I've got to label this feasible region with an R. So believe it or not, if you don't do that, you will not get the mark. So there's 3 marks available for a question like this. And in this case, you're going to get an M1 mark for drawing a line with gradient 1 or gradient 5. You're going to get another mark, a follow-through mark, for drawing either of these 2 lines correctly. And by correctly, it's a follow-through mark, so as long as you've drawn the lines you've got. So that's going to be an A1. And finally, you get a final accuracy mark for a correct answer, including the letter R. Okay, and last but not least, we need to use the objective line method to determine the optimal point. So we want to maximise p is equal to 3x plus 5. But to draw this line, it's a bit tricky to conceptualise. So I'm going to rearrange this equation. I'm going to get that 5y is equal to p subtract 3x, or y is equal to negative 3/5 of x plus p over 5. So I'm going to get a gradient of negative 3/5. So I'm going to try and draw my objective line on. And if the y is equal to negative 3/5, it's quite a shallow line. It means that my x value is going to be 5/3 of my y value if I cut through the axes. So I'm going to try and do one of these values. So I'm going to consider the point 25. I'm going to consider point 15. And I'm going to draw my objective line just through these 2 points. So 0, 15 lies on the line. If I substitute in, it lies on a line. So if I substitute in 0 and expect an output of 15, that means that P must be 75. And similarly, if I substitute in 25, I'm going to get negative 75/5. And if I added on 75/5, then y would be 0. So these are on the same line. So I'm going to try and draw a line through the 2 points. And we've just got to try again. One note is a bit tricky with drawing straight lines. There we go. So I've drawn the objective line on. You probably want to continue it off the diagram. And if I want to maximise P, I need to keep increasing this line further and further up. And if I do that, I'm going to get this point here. And that point is the intersection of 2 particular lines. It's actually the intersection of 2 lines that we began with. It's the intersection of x plus y is equal to 30 and the line 2x plus 10. So this line here. And we can solve those simultaneously. So I'm going to try and solve those simultaneously now. So we've got that y is equal to 2x plus 10 and x plus y equals 30. So I can substitute this first equation into a second one and get x plus 2x plus 10 is equal to 30. Which is going to give me 3x plus 10 equals 30. So 3x is equal to 20 and x is equal to 20 over 3, which is equal to about 6.67. That means that y must equal 30 subtract x by rearranging this second equation. So y must equal 90/3 subtract 20/3, which is equal to 70/3, or approximately 23.33. So, have we found a solution to this problem? Well, unfortunately, we've not found a solution just yet. Because we can't have a decimal number of fish. So we need to consider the integers around this solution. So we've got a solution that's not quite an integer. So you've got a solution 20/3 and 70/3. Or approximately 6.6 and 23.3. Maybe say 6.7. So the x value smaller than this is going to be 6, and the x value larger than this is going to be 7. And similarly, x value 6 and x value 7. And then the y value smaller is going to be 23. And y value larger is going to be 24. But we need to consider whether or not each of these points satisfy the inequalities that we've got. So first of all, we've got x plus y is less than or equal to 30. And x plus y is less than or equal to 30 is true for 624. They add up to 30. It's true for 623. They add up to 29. And it's true for 723. They add up to 30. But 724 adds up to 31. So we're going to eliminate that vertex. It's unfortunately not possible. We've also got another criteria. Y has to be less than or equal to 2x plus 10. And these are the only two criteria we're considering because it's the intersection of these two lines, so it's these two criteria that are going to make or break the solution. So is y less than or equal to 2x plus 10? So 623, 2x is 12 plus 10 is 22. 23 isn't less than or equal to 22. 7 times 2 is 14, plus 10 is 24. So y is smaller than that. So we get a double tick there. And finally, 624. Well, we've made y bigger than 623, and we've not changed x. So y is definitely not going to be smaller in this case. Finally, 724. I am going to consider it despite us ruling it out before, just to see whether it works. And if we multiply the x coordinate by 2, we're going to get 14. And if we add 10, that gives us 24. Our y coordinate of 24 is less than or equal to 24. However, there's only one solution that satisfies both of these. And that solution is x equals 7 and y equals 23. And in that case, our profit, we're assuming this is profit. Does the question actually say this is profit? It does, the total value of a fish. So we're wanting to maximise the value. P is equal to 3x plus 5y. Yes, it is. So P is equal to 3x plus 5y. So we can substitute in our x and our y. The total value is 3 times 7 plus 5 times 23. So this is equal to 21 plus 115. And if we try adding 21 and 115 together, we're going to get £136. So let's make sure we've actually solved the question. Asked to find the maximum total value of a fish, stating the optimal number of orange fish and the optimal number of blue fish. So the maximum total value, and we are going to write this out. Maximum total value is £136, and this is with 7 orange fish and 23 blue fish. So with that, let's see how the marks are broken down for this. So you'd have got 1 mark for drawing the optimal line, 1 mark for the optimal point, which you should write down. So actually, we should be writing down the optimal point, and we have, so that's going to be an accuracy mark. And then a method mark for considering at least 2 integer coordinates around the point. So we do get the dependent method mark. And then finally an accuracy mark for stating the maximum total value and the total number of each fish. Thank you for watching, and for now, goodbye.